Now we have an interesting question in question number 15, and it says number of positive solution to this equation e to the power x sin x, and this is log x plus e to the power under root x plus 2. Now if we look at these two functions separately, then first function is suppose fx, which is e to the power sin x, and second function is suppose gx, which is log x e to the power root x plus 2. Now we know that e to the power sin x will oscillate within the bounds of e to the power x. So it'll be this graph, and if we look at g dash x, it'll be 1 upon x plus e to the power root x upon 2 root x, and since domain is x is greater than 0, we are looking at number of positive solutions. So this function will be an increasing function. So we know graph of fx, we also know graph of gx, but the problem here is we can have so many possibilities. We can draw this graph like this, we can draw it like this, we can draw it at some point, it may be above the graph of e to the power x. So this problem is not that simple. So the first part of this problem will be to define the relation between e to the power x and this other function log x plus e to the power under root x plus 2. So what we'll do is, first we'll find number of solutions of this equation. E to the power x equals log x plus e to the power root x plus 2, or e to the power x minus e to the power root x, and that will be equal to log x plus 2. Now here too, what we'll do is we'll consider them as two functions. Suppose this first function is f1x and this second function is f2x. Now this f1x is e to the power x minus e to the power root x. Now we know that when x lies between 0 and 1, e to the power x will be less than or equal to e to the power root x, or e to the power x minus e to the power root x will be less than or equal to 0, and when x is greater than 1, then in that case e to the power x will be greater than e to the power root x, or e to the power x minus e to the power root x will be greater than 0. So, and what we also know is f1 0 is 0 and f1 1 is also 0. So if we look at graph of this function fx or f1x, it will be drawn something like this. So this is 0, this is 1, and that's the graph of f1x, and that is e to the power x minus e to the power root x. Now this f2x function, it is simply log x plus 2, and basically this is y minus 2 equals log x. So basically we have to take the graph of log x and then we have to shift it 2 units upward. So this graph will be drawn like this. So it will intersect at 2 points. So this is the graph of f2x, which is log x plus 2, and it will have 2 roots, say alpha and beta. So we have 2 roots, alpha and beta, where alpha is less than 1 and beta is greater than 1. So this equation will have 2 real roots. Now, how is this information going to help us? Now what we'll do is, we'll restrict our analysis when x is greater than or equal to beta. Now when x is greater than or equal to beta, in that case, graph of f1x will always be above the graph of f2x. So when x is greater than or equal to beta, there f1x will always be greater than or equal to f2x, or we can write e to the power x minus e to the power root x will be greater than or equal to log x plus 2, or e to the power x will be greater than or equal to e to the power root x plus log x plus 2. So from here what we can do is, if this is beta, then after beta, graph of e to the power x will always lie, or will always be above the graph of e to the power root x plus log x plus 2. Now after establishing this fact, now we can come to our original function, which is fx, and it was e to the power x sin x. Now for e to the power x sin x, the bounds are e to the power x and e to the power minus x. So we draw e to the power x and e to the power minus x. Now at beta, we are not sure about the phase of sin x. I'll take any random phase and then we'll draw the graph of sin x. So every time when this graph is going up and coming down, it is going to intersect this other line, which always is going to lie below the graph of e to the power x. So that means this equation fx equals gx is going to have infinite roots. So basically, the number of positive solution to this equation is infinite, and that's your option D.